Hi guys, I hope you had a great weekend. I'm just coming on here to begin the new unit with you guys, which is conditional trig equations and how to solve them. So today I'm going to do day 1 notes, and the homework will be part 1 homework from the Unit 13 packet, which is posted on Google Classroom. One thing I wanted to mention about this unit is that we are treating this as solving equations. These are no longer identities, but equations where we actually want to solve for x. And keep in mind what the directions here are telling us. It says solve for x, where x is between 0 and 2 pi. It includes the 0, but not the 2 pi. So essentially what we're looking for here is the angle, if we're staying between 0 and 2 pi. And also keep in mind that this means that we are going to work in radians, okay? So just keep that in mind that for this unit we are in radians. Part of this unit is calculator, so I would suggest having a calculator nearby to help you out with some of the problems. I will tell you which problems are calculator problems. The first few will not be, but the last example in this lesson will be a calculator problem, and we'll do that one together. Feel free to stop this lesson at any point and kind of like pause and try the problems on your own if you want after I go through a couple of the examples. But I'm just going to kind of teach through each example here. So in example 1, basically the way you want to look at these equations is as if they are quadratics, because we have a sign squared here, we have a sign, and then we have a constant. And so anytime we want to solve quadratics, the idea is to get one side equal to 0. So I would go ahead and subtract the 1 over. So we have the quadratic 2 sine squared x minus 1 equals 0. And if you guys don't like the way this looks, you of course can do a substitution where you let like capital A equal sine x, so that you would get 2a squared minus a minus 1 equals 0, and you can go about it that way. I'm not going to do that for this unit just to save myself some time, but if that strategy helps you, then by all means go for it. So once we have our quadratic, we have to decide, is this factorable or not? And this one indeed is. And you should get the factors to be 2 sine x plus 1 times sine x minus 1 equals 0. And just like we would with the normal quadratic, we would set each one equal to 0 and solve. So for this side, we would get sine x equals negative 1/2. And for this one, we would get sine x equals positive 1. And so as you go through and you solve this, we've actually done problems like this probably way back in like unit 7. But basically, remember, in order to solve for sine x equals negative 1/2, what you're doing is you're first taking into consideration a smart trig class and deciding what quadrants sine is going to be negative in, which would be quadrants 3 and 4. And then the 1 over the 2 should remind you of your 30, 60, 90 triangle. Okay, and the angle when I take sine, opposite over hypotenuse, that gives me 1/2 is 30 degrees. But again, remember, we are working in radians. So 30 degrees in radians is going to be pi over 6. And again, I put it in quotes because that's not our actual answer, because I need what pi over 6 is in the third quadrant and what pi over 6 is in the fourth quadrant. So in the third quadrant, if you remember, what you have to do is you have to do pi plus pi over 6, or 6 pi over 6 plus 1 pi over 6. That gives us 7 pi over 6. And then in the fourth quadrant, you have to do 2 pi minus pi over 6, or 12 pi over 6 minus 1 pi over 6, which gives us 11 pi over 6. So these two are definitely two answers. But then remember, we still have to solve where sine x equals 1. Well, remember, technically this is the ratio 1 over 1. And the hypotenuse and the side of a triangle cannot be the same length. So this has to be an angle that is on the axis. And when we are on our axis, remember this is our y over r, so it's really where y equals 1, and y equals 1 right up here, and that's where x is going to be pi over 2. And so those three would be our answers for that particular problem. Okay. Then I have another problem over here that says cosine x times cosecant x equals cosine x. A lot of students are tempted to sort of divide through both sides by cosine x, but remember when you're solving equations, you never want to divide by the variable because you will lose answers that way. So anytime you're tempted to do that, really what you want to do is you want to subtract the cosine x over, and you get cosine x cosecant x minus cosine x equals 0. And then what ends up happening is the cosine x ends up becoming a GCF. You would just factor it out, and you're left with cosecant x minus 1. And now you just set each one of these factors equal to 0. So cosine x equals 0, and cosecant x equals 1. Okay? So again, cosine x equals 0. That means that your angle has to be on the axis. Remember, cosine refers to your x variable. This is x over r. So wherever x is 0, which would be up here and down here. And so those angle measures again are pi over 2 and 3 pi over 2. Okay, and where cosecant x equals 1, well, if you don't like thinking about the reciprocal functions, you can always flip both sides. So if you didn't want to think about where cosecant x equals 1, you can also think about where sine x, I took the reciprocal of this side, so I have to take the reciprocal of this side, which also happens to be 1. So where sine x equals 1, well, that's up at pi over 2 as well. So there's no need for you to write the answer twice if I already have it over here. So just these two are our final answers for that one. Okay, so moving along to example 3. This is the part where for these two examples, they're very similar to numbers 1 and 2. So if you want to go ahead and pause the video and try these on your own, you can certainly do that. But I'm going to go ahead and show you the process for each one of these. So for number 3, you need to be very, very careful here because this looks like a quadratic right off the bat, but you need to notice that this guy is in terms of cosine and this guy is in terms of sine. So the idea is that we want to get both trig functions to be in terms of the same variable. So it's easier to turn cosine squared into sine. This is what I like to call the anchor of the problem. Because it tells you what trig function to center the problem around. Sine x can't be changed. Cosine squared x can definitely be changed. So we would change this to its Pythagorean identity, which says 2, and then parentheses, this becomes 1 minus sine squared x plus 3 sine x minus 3 equals 0. And now I'm going to distribute the 2 through. So we get 2 minus 2 sine squared x plus 3 sine x minus 3 equals 0, and then combine like terms. So we get negative 2 sine squared x plus 3 sine x minus 1 equals 0. Now, I don't know about you guys, but for me, whenever I factor, I don't like when my leading term is negative, so I'm just going to divide everything through by negative 1 and change all the signs. So that becomes 2 sine squared x minus 3 sine x plus 1. And now I have to factor that guy, okay? And so those factors end up being 2 sine x minus 1 times sine x minus 1 equals 0. And again, you set each factor equal to 0 and solve. So here we would get sine x equals 1/2. And here we would get sine x equal to 1. And here you notice that the ratio is positive 1/2. Sorry about that. So if it's positive 1/2 when we do a smart trig class, then that means you're in quads 1 and 2 this time. And we already discussed from example 1 how the ratio of 1/2 gives us 30 degrees, or the radian measure of pi over 6. So here we would get, well, in quad 1, it's just whatever your radian measure actually is. So pi over 6 is one answer. And in quad 2, if you guys remember, you have to do pi minus pi over 6, or 6 pi over 6 minus 1 pi over 6 to give us an answer of 5 pi over 6. So these are two answers here. But then we have the equation of sine x equals 1 to solve. So again, where sine x equals 1, we did this in previous examples, that is where x is pi over 2. And so all three of those would be our answers for this problem. So you have to be really, really careful. Make sure when you're starting off the problem that all the trig functions are the same. Sometimes your eye can trick you into thinking they are, and they're really not. And then you might end up with the wrong answer. So for number 4, this is similar to example 2, where, again, I don't want to divide through by cosine because I don't want to divide by a variable. So instead, I'm going to subtract the 2 cosine x over, and we get cosine x sine x minus 2 cosine x equals 0. And again, cosine x ends up being a GCF, so we factor it out. We get sine x minus 2 left over equals 0. And then we set each factor equal to 0. So here we get cosine equals 0, and here we get sine x equals 2. Okay, so cosine equal to 0, again, we did that in a previous example. Remember, this is the ratio x over r, so it's really where x is 0, which is up here and down here. And those radian measures would be pi over 2 and 3 pi over 2. And then where sine x equals 2, well, remember, this is the ratio 2 over 1, which would be y over r. But again, the side length of the triangle cannot be bigger than the radius of the triangle or the hypotenuse of the triangle. So actually, this is not even possible at all, right? That's one way you can think of it. This guy will yield no solution for this part. The other way you can think of it is, if you remember the boundaries that we talked about for sine, sine always has to be in between -1 and 1 inclusive. So if you have a number outside of those boundaries, it's automatically going to be no solution. So our only two answers here would be pi over 2 and 3 pi over 2. So number 5 is a little bit of a different example, where we have cotan squared x equals 3. And again, the idea here is to first isolate the trig function. So I want to get rid of this squared here. So I'm going to square root both sides of the equation. Be careful when you square root. You need to remember the plus or minus sign. And then we're going to go ahead and say that this is where cotan x equals plus or minus root 3. And again, if you don't like working in terms of the reciprocal functions, you can always flip it. So this would be where tan x equals plus or minus 1 over root 3. That might be a little bit easier for you guys to think about. And we have to think about what quadrants we're in, so we do a smart trig class. However, because we're both positive and negative, that means that you're in all 4 quadrants, right? Because you want where tan is positive, which will be to the quadrants, and negative, which will be the other 2 quadrants, okay? And then 1 over root 3, that ratio should remind you of your 30, 60, 90 triangle, so you draw that up. And which angle, when you take tan of it, which is opposite over adjacent, 1 over root 3, gives you 1 over root 3, that's 30 degrees, or your radian measure of pi over 6. But we need that in all 4 quadrants. So looks like I'm going to get pi over 6, 5 pi over 6 for quad 2, 7 pi over 6 for quad 3, and 11 pi over 6 for quad 4. And again, if you need a reminder of how to get the equivalent radian measures per quadrant, I'll just do this quick thing. Remember, in quad 1, it's just theta. In quad 2, it's always pi minus theta. Quad 3, it's pi plus theta. And quad 4, it's 2 pi minus theta, where theta is just your reference angle here. So That's just a quick little reminder there. Okay, so that's how you would do something like number 5. And then lastly, number 6, this is our calculator problem. So this is the one where you might need to go ahead and grab your calculator. But again, you see that it's sort of set up in quadratic form, right? You have the squared, you have the 7 sine x, and then you have the constant, and it's set equal to 0. The first thing I would do if this were me is I would try factoring this normally, and it does factor normally, in fact. And so when we factor it, we get 5 sine x plus 1 times 3 sine x minus 2. Those are the two factors. So however you guys manage to factor, go ahead and find a way that works best for you. And then you set each one equal to 0 and solve for sine x. So here we would get sine x equals negative 1/5, and here we would get sine x equals 2/3. So from here, I'm going to decide, first of all, is this doable, right? Is sine x allowed to be 1/5? Well, negative 1/5. Well, negative 1/5 is in between negative 1 and 1. So yes, this is a doable problem, right? So again, I would think about what quadrants I'm in. And this time sine is negative, which means I have to be in quad 3 and quad 4. So because sine is negative, I'm in those quadrants, but the ratio is 1/5. That doesn't necessarily refer to one of our special right triangles. So here's where the calculator comes into play, okay? So I'm going to pull up my calculator here, so just bear with me. Okay, and basically what we do is, what's very important to remember here is that the negative in the 1/5 is just to tell you what quadrants you're in. Once you go to put it in the calculator, you never input a negative ratio. And I'm going to say that again because it's going to be true for all of the problems in this unit. Anytime you input stuff into the calculator, you never input a negative ratio. So once you determine what quadrant you're in, basically, if I go back to my notes, sorry about that. In order to solve for x here, if you guys remember, we would have to inverse sine both sides of the equation, but basically what I'm inversing is positive 1/5, not the negative. The negative is just to tell me I'm here and here, okay? So I'm going to go to my calculator. I'm going to inverse sine positive 1/5. Make sure you are in radian mode, by the way, okay? And we hit second sine 1 divided by 5. And we get our answer. Now, the calculator will always give you your answer in quad 1. But keep in mind, we are not in quad 1. We are in quads 3 and 4. So if you want to store this as x, just so you have the exact decimal, and then go ahead and find it in quad 3, which we know we would have to do our stored x plus pi for quad 3. Okay, so our answer there is going to be 3.343. I'll take it to 3 decimal places, so 3.343 there. And then also in quad 4, which we know we would have to do 2 pi minus our stored x, which would give us 6.082, okay? So those would be our two answers for that side of the equation. So we get x equals 3.343 and x equals 6.082. Okay, and we kind of take the same approach for this second equation that we have to solve, where sine x equals 2/3. Again, you determine what quadrants you're in, and this time our ratio is positive, so we have to be in quads 1 and 2. And then I go ahead and I inverse sine both sides in order to solve for x. And again, 2/3 is an acceptable ratio because it's in between -1 and 1, so that we know that we're allowed to do that. Okay, and then I input this into my calculator. So I'm going to hit second inverse sine of 2 divided by 3. And again, that gives me my answer in quad 1, which is 0.730 if we round to 3 decimal places. Remember, we were already in quad 1, so this is an actual answer here. And then I'm also in quad 2, so I'm going to store this as x. And then for quad 2, we have to do pi minus our stored x, and we would get 2.412 if we round to 3 decimal places. So again, go back to our notes. We would get x is 0.730 and x is 2.412. And all 4 of those answers would be answers for something like number 6. So I hope that this video helps you with homework part 1. Please go ahead and try those problems and pay attention to the due dates that I'm going to be posting on Google Classroom of when that will be due. And, good luck. We'll see how this goes. See you guys.